702.
The Naked Scientist.
Chris, good morning.
Hey, CBS, good morning.
You've been talking to an Australian researcher about an interesting paper in relation to great white sharks.
Yeah, and this work was done in South Africa in the Western Cape. Wonderful story. What Ollie Jewell, who is a researcher at Murdoch University in Perth, has done is, for the first time, managed to strap cameras onto great whites. Now, this is quite a feat because you don't want to harm the animal, but you do need to get close enough so that you can then strap on a camera with a temporary clamp which they put around the dorsal fin of the animal, and it's got a corrodable attachment. So as the animal swims through the seawater, slowly the clamp falls to pieces and eventually it detaches and the camera floats to the surface, and it's got a transmitter on it and a satellite tag as well, so they can then go and find it and then they retrieve all the data off the camera. And what this is enabling them to do is for the first time actually track where these animals go underwater and what they see. And they were very interested, for instance, in how the animals interact with kelp forests, because people for a long time had said great whites probably won't go into kelp forests because although the seals along the Western Cape will go in there, the whites won't be able to navigate, they won't be able to see properly, so they won't go in there. This totally disproves that. But it's a real initial look-see as to how we can do this sort of thing, because one of the most important aspects of conservation is how do you conserve something that you don't understand? So in order to conserve these animals, which are on the watch list, they are threatened, we need to understand much more about their behaviour, where they go, what they do and how they do it. So getting literally, I would say a bird's eye view, but it's an underwater bird's eye view of what these animals do and what they see is really important. And this lovely paper in Biology Letters, I've just been talking to Ollie Jewell about it, and he said there are examples, for instance, of the animals responding and reacting to things they can see. And he said there was one particular bit of footage he's got where the shark's swimming along and then all of a sudden starts to move towards the surface as though something's caught its eye. And when it does get close to the surface, you can then see on the camera that actually it's a seagull that the animal has seen from underwater and has completely surfaced to go and see if it can have a look at this bird, thinking maybe I'll eat that. So it's also teaching us about maybe how the visual systems of these animals work as well, so you can match up what the camera's seeing with what the animal must be seeing and how it responds. So lovely paper and a nice initial look at how we can actually non-invasively get a view and a better understanding, a richer understanding of how a pretty enigmatic species, which are nonetheless endangered, go about their business.
Stunning. George, good morning. Welcome to the show.
Morning, Eusebius, and good morning to Dr. Chris. I would like to know what progress has been made so far with the ITER tokamak experiment in France, where investigation of atomic fusion as opposed to atomic fission, which will help us in power stations. I talk under correction, but I doubt if South Africa has ever contributed any money to the research, so we won't be able to share in the fruits.
Hello, George. Well, I think it's fair to say that everyone will share in the fruits of scientific endeavour because that will make the world better, and especially things which will help us to cut our carbon footprint. So if we are able to realise fusion power, this is a lot less environmentally harmful than other ways of generating electricity, for example, because the waste products are minimal and the infrastructure will be minimal. And that means that everyone benefits from a cleaner environment and the provision of cleaner, cheaper energy and technology. Now, how they're getting on at ITER, and ITER stands for the International Thermonuclear Experimental Reactor. It's in Cadarache in France. They're trying to develop ways where we could take materials and ram them together very hard, and by squeezing small things together hard, you can make small things become bigger things. And when this occurs, the nuclei at the cores of the atoms join together and make a bigger nucleus, and you get this release of energy because some of the binding energy from the two nuclei is released. And you end up with a bigger nucleus that's more stable than the two that you started with, and that increased stability is the energy you see. Now, we know this process can work, and the reason we're pursuing this as a potential energy generation provision is that the sun that warms the Earth and has been there for 4.5 billion years is powered by nuclear fusion. The sun started out almost exclusively made of hydrogen, and under the enormously high temperatures and pressures is slowly squeezing 4 atoms of hydrogen together to make an atom of helium, for example. At the same time, it's then starting to make bigger and bigger chemicals by taking those bigger nuclei and squeezing those together. So we know this process can work because we can see it happening for ourselves. The problem is how you harness that down on the planet's surface. The sun has the advantage of being massive, and not just in terms of its extent in the sky, but it has a lot of mass. That means it has an enormous amount of gravity, and if you have a lot of gravity, you can squeeze things together very hard and create the pressures needed to make atoms fuse. Down here on the Earth, we don't have a sun-sized reactor in order to do this, so we have to find other ways of doing it. One way to do it is to use things like laser beams, for example, to push materials together very hard by almost causing a sort of domino effect where they shock into each other extremely hard. That's one way that researchers both in America and France are trying to do that. The other problem is that the sun at its centre is millions of degrees. We need to create temperatures of millions of degrees down here on Earth, but then if you have something at millions of degrees, it would melt its way out of the thing you've got it in. So you have to confine the reaction somehow. And so we're looking at ways of making things like magnetic fields that can constrain and confine the plasma that you're reacting together to form the fusion reaction. That also is complicated. So these are many problems that need to be solved, and they're at the stage where you can get short-lived fusion reactions, but we haven't got a self-sustaining one yet where you can put energy in and you get more energy out than you put in to run it. But these are all problems that are potentially surmountable with enough time and technology and effort, so it's definitely worth pursuing. We know it can work theoretically. It's a question of harnessing that power down here on Earth, but we're not there yet.
Andrew, good morning. What is your science question?
CBS, good morning. Good morning, Dr. Chris. I would just like to find out, I was recently watching a program on television, and they extract water from the humidity that's available in the atmosphere. And I was wondering, is that a lot different from the water that you would get out of a spring or out of a dam? And then the other part of the question is, would water that is no pH, obviously, and there's no bacteria in there, would it be different and more damaging or not to you than the water that you get from a spring or a dam or something like that?
Hello, Andrew.
Thanks, Andrew. Thanks for that.
The answer is that water is water, H2O, and so in the pure sense, it's not going to make any difference to you where it comes from if it's pure water. There is water in the air because the air has humidity, and it's possible to capture that, and there are various ways of doing that. And clouds are essentially where the water in the atmosphere is coalesced to form lots of hydrometeors, ice crystals or droplets of water, which they then rain down on the Earth's surface. When that water comes down through the atmosphere, it can absorb some of the gases in the atmosphere. It dissolves some CO2, it can dissolve some other oxides of sulfur and nitrogen, for example, and that's what causes acid rain. It can also dissolve a bit of oxygen. If you have pure water coming out of a stream, it will have, I say pure water, it will also have come down through the atmosphere and have some of those things in it, plus it will have filtered through the ground, so it will have some salts in it. If you trap water just from the air, it will probably have a lower salt burden than water that's removed from a river, but at the end of the day, it's still water and it will keep you alive. No problem. There's no risk of putting your health in jeopardy in that respect. Yes, river water is going to have a higher microbial burden in it, probably because there are fewer microbes, not no microbes, because there are microbes actually that live in clouds. There's a species of Pseudomonas called Pseudomonas syringae that actually makes its whole life cycle around making water form small droplets in clouds, so it gets rained down onto the Earth's surface. So there is microbial action in rainwater, but there will be more in river water. But water's water, and as long as you get a drink, that's the main thing.
Tony, good morning. Welcome to the show.
Morning. Is it your CBS?
Yes, it is. What is your question for Chris?
The question for Chris is, given our current knowledge of artificial intelligence, is it probable that computers might develop consciousness? And if so, how would we be able to measure this consciousness?
Okay, interesting question. Chris?
Yeah, it's an interesting philosophical question, this one, because we're conscious. We have some idea as to who we are, our place in the world, and our own mortality. Is it possible to make a computer that also has a sense of what it is and its own mortality? Well, the answer is probably yes. You probably could write a computer program. In fact, as these systems become more artificially intelligent, part of that is going to be learning that they exist for a reason, why they exist, and what keeps them existing. And therefore, one ends up with this ethical situation. If I have a computer that now knows it's alive, or a robot that knows it's alive, if I turn it off, I'm killing it, aren't I? And therefore, does it have rights? And it's interesting that these were the kind of questions that were being debated on Gene Roddenberry's Star Trek: The Next Generation, where they had an android person in the programs about 25, 30 years ago. And it's interesting that we all thought at the time, oh, this is a bit daft. All these people were hand-waving and worrying about robots having feelings, because that's never going to happen. But here we are, about 25, 30 years later, we have most of the technology, apart from a warp drive, obviously, that would be nice. But we have most of the technologies that were being used to wow us with 30 years ago on Star Trek. We have them, including devices that do have some semblance, potentially, of intelligence and consciousness. So at the moment, it's very much up in the air. What do we do with these devices? And if they do become conscious, therefore they know that they're mortal, and that if we pull the plug that will kill them, therefore will they start to take steps to prevent us from pulling the plug? And this is the whole question about whether or not artificial intelligence will take over the world. And I think Stephen Hawking, who said it was a major threat. Artificial intelligence and the rise of the machines is a major threat to humanity. And he was right about a lot of things. I hope he's not right about this one, though.
702. The Naked Scientist.
21 minutes after 10, we're talking science. Any questions from science that you want to put to Chris? 011 883 0702. Hannah, good morning. Welcome to the show.
Hello, good morning.
Go ahead. What's your question for us?
Okay. My question is, there has been a lot of conspiracy theories about the Earth, whether it is round or flat. I just want to know why people think that the Earth is flat. And also, what is your opinion on this matter? Do you think that the Earth is flat or round?
Hello,
Sorry,
Hannah.
Chris.
I want to know why people think the Earth is flat as well, because we've known for actually thousands of years. Eratosthenes, who was active doing his own forms of geometry and maths in Egypt a couple of thousand years ago, knew this, and he was able to prove the radius of the Earth. He measured the size of our planet. He knew it was a big ball in space even then. So why, a few thousand years later, we're still obsessing about the idea that the Earth is flat? I don't know where this is coming from. A quick look at the universe around you will hopefully disabuse even the most ardent flat earther of the notion, because if you look at the sun, it's a ball. If you look at the moon, it's a ball. If you look at Mars, it's a ball. If you look at the surface of Mars that we're driving around on with our rovers that we've put there, it's a ball. If you look at the Earth from Mars, it looks round. So why there's all these people who think that the Earth is flat? I really don't know. And if you go to the nearest beach and you watch a ship sail over the horizon, you will see that the ship slowly disappears, but it doesn't disappear all at once. You will see the ship disappear from the bottom up. In other words, it sails over the curvature of the Earth, and only the tallest parts of the ship remain visible at the last moments before it ducks below the horizon. So the Earth is definitely not flat, it's definitely a ball, and everything we see around us is also a ball. And if you ask anybody who's been into space, on the International Space Station, for example, doing about 15 orbits of the Earth every day, so every 90 minutes they're going around the Earth, they will tell you from space they can see a ball. So hopefully that's laid that one to rest.
Harry, good morning. Your question?
Yes. Hi. Can you hear me?
Yeah, ball.
Okay. Yeah, okay. So my question is, I was driving through Joburg the other day, and then I looked on the horizon. I saw white clouds and grey clouds, like dark grey clouds. And they all seem to be at the same level. Why are some of them grey or dark grey and some of them are white? It doesn't make sense to you. I know back in school 20 years ago, the cumulonimbus clouds, or those thicker ones, and the cirrus ones, or the higher ones, but these are like those thick, like cumulonimbus, those big, thick clouds. Some were white, some were grey, and it was all patchy. Like,
I hope, by the way, Harry, it didn't trigger bad geography memories.
Yeah, hopefully not. I don't know. I got an A for geography, which is scary if I'm wrong.
Chris?
Harry, good morning. The answer to this question is the reason clouds are the colour they are is because they contain a lot of water droplets and ice crystals. And those droplets are tiny. They have the effect of reflecting all of the different wavelengths of light that are hitting them back at you. And that means that because you're seeing all the different colours reflected at you, they look white. It's exactly the same reason that frost and snow look white. But equally, if you've got a very dense cloud with lots and lots and lots of those droplets, then they're going to look darker because the amount of light that gets scattered back into space is going to be higher. Because remember, the cloud looks white because light is hitting it. Well, if the entire sky is blanketed in this thick smog of these huge great clouds, much less light is coming through, so that much less light is then going to go onto the surface of the cloud and bounce back at you to make it look white. So it's going to look darker. So in patches of cloud that are very dense, patches of cloud that have lots of water droplets which have reflected lots of light back into space, that patch of the cloud is automatically going to transmit less light, so it's going to look darker, and it's also going to have less light because the sky is all like that, hitting the surface of the cloud to reflect down to the earth to see you, so it looks darker still. So that's the reason. It's the higher density of the cloud. There are more droplets in there reflecting more light back off into space in the opposite direction, so the cloud looks greyer because it's less well lit, it's less well illuminated.
We've got a voice note with a question. Let's have a listen to this one.
Morning. Question about the black box. How is it that the flat box is so strong that it cannot be damaged, but flights are not made with the same material? I listen on the radio. Thank you.
That's a lovely question. I've always wondered. I'm glad someone asked that question, Chris. Can I tag on a second part to that question for my own curiosity? What is the data that these things contain anyway that allow researchers, when they found it, to be able to make so many useful deductions?
Well, it's a bit of a myth that it's black because black boxes are actually red. They're bright red. There are a couple of them in each aeroplane, and they're made red for obvious reasons because they're easy to see, so that they can be easily retrieved. The reason that they're so resilient is because they're built of material that's fireproof and waterproof. So the idea is that it doesn't matter what you throw at them, whether they get set on fire, whether they're sunk underwater, subject to extreme pressure, they're made of this very, very resilient material to defend the electronics inside, which is recording flight data. Now, what they're monitoring is what conversations are going on in the cockpit and between the pilots and the ground, also important parameters about the flight, where the controls are set to, what different performance attributes and parameters are with the engines, for example, so that in the unfortunate situation where there is some kind of disaster, that we can begin to piece back together what probably happened. Because the airline industry has one of the most impressive safety records of any industry. And part of that is because there's enormous diligence and careful scrutiny of everything that goes on, but also there is forensic scrutiny of whenever there is an accident or a disaster. And it's all because we have this very rich source of data from these black boxes. You can't make the entire aeroplane out of that because aeroplanes still have to carry people, and people are squishy. And when we actually have a crash, part of the injury is because you're going from doing hundreds of kilometers an hour to almost zero in a fraction of a second. And that deceleration has a catastrophic effect on the human body. Our tissues are soft, they can bend and move, but they are not sufficiently elastic that they can withstand that. You can withstand electronics to withstand that. You can design electronics to withstand that, but you can't make a human withstand that. So even if you had an aeroplane that was built of the same stuff a black box was, the people inside would still decelerate at the same speed that the plane was decelerating when it hit the ground. So they would still nonetheless be very profoundly injured. So you'd have an intact plane and still have the same outcome. Loads of people who were dead. So that's unfortunately not a solution to the problem. Making safer aeroplanes and trying to find out why things go wrong on the rare occasions they do is the best way to make a safer industry and keep more people alive. And the airline industry do it impressively well.
Sizwe, very quickly, let's squeeze in your question. What is it?
Okay, my question is like when you take a shower and it's actually like a hot shower, you tend to be a bit dizzy. So I thought like the steam actually carries 2 hydrogens and 1 oxygen. Why? The oxygen is already there. Why do you still feel dizzy and all that?
Okay. A hot bath or shower rather, why might it make you dizzy, Chris?
The reason for this is when you get into a very hot bath or hot shower, it raises your body temperature. And when your body temperature goes up, because you're not losing as much heat to the environment, because the environment of the hot shower or bath is hot, so rate of heat loss falls. When you get very hot, your body compensates for the increasing temperature by diverting more blood from the centre of your body in your core to your peripheries by opening up blood vessels in your skin surface, fingers, toes, and so on. Now, if you're pushing lots of blood into the skin surface, your blood pressure can fall, and the amount of blood critically returning to your heart can fall. So when you stand up quickly out of a hot bath, for example, the amount of blood flowing back up your veins to get to your heart, to be pumped up to your brain, temporarily dips a bit. And that dip temporarily, before various reflexes kick in and tighten up the blood vessels to put the pressure up again, makes you feel a bit woozy and dizzy, because it temporarily robs your brain of its blood flow and therefore its oxygen supply for a very short time. And it's that temporary robbing of oxygen and blood flow that causes you to feel woozy and giddy, because your brain has and your eyes have one of the highest metabolic rates of all the tissues in your body. Despite weighing only about 2% of your body mass, your brain accounts for 20% of the oxygen that you're consuming at any moment in time. So it's so metabolically active, and it gets that oxygen from blood. And if the blood pressure drops temporarily, then the perfusion drops temporarily, and therefore you feel temporarily a bit giddy.
Stunning as always. Thank you, Chris. We'll talk again next week.
I'm looking forward to it already. Thanks, everybody. See you soon. Bye-bye.